Okay, so the question here is, when can I plug in to find the value of a limit? Okay, let's look at a couple different examples. Suppose we have the limit as x approaches 2 of x cubed minus x squared plus 5. And we also have the limit as x approaches pi of sine of x. And one more for good measure. Suppose we have the limit as x approaches negative 1 of the rational expression x squared plus 3x plus 2, all of that over x plus 1. Okay? And let's look at these three examples in turn. Well, I would really love to be able to plug this 2 into this expression to evaluate the limit. Okay? And sure enough, I can do that. And what lies at the heart of being able to do that is the notion of continuity. Okay? If we know that a function is continuous at a specific point, let's call it x equals c, then we know that f of c, okay, so that's the value we get out when we just plug in c, f of c and the value of the limit as x approaches c both exist and agree in value. So if I want to know what the value of this is, I just need to figure out the value of this. And finding the value of this is easy. I just plug in c. Okay? So to be able to tell whether or not I can plug in 2 into this expression to find the value of the limit comes down to knowing whether or not this function is continuous at this x value. But one nice thing about polynomial functions, this is a polynomial function, remember, is polynomial functions are continuous everywhere. And so in this particular case, it is certainly continuous at x equals 2. And so I can plug it in. So I get 2 cubed minus 2 squared plus 5. Of course, that's 8 minus 4 plus 5. That's 4 and 5. That's 9. Okay? So that is the value of the limit. And again, graphically speaking, we're talking about a point of continuity there. A point of continuity at 2, 9. Remember, this is what x is approaching, and then this is the height, or y value, approached. Now, the same thing goes down here. As x approaches pi, well, can I just plug in pi and crank this out? It depends. Is sine of x continuous at pi? Well, sure it is. Just like polynomial functions are continuous everywhere, sine of x, cosine of x, those two functions are also continuous everywhere. So I am free to plug in the pi and drop my limit here and just say this is sine of pi. And of course, a real quick reference of the unit circle. Remember, here is 0, here is pi. We're talking about this point right here. The sine is the y-coordinate. Y-coordinate there is 0. And now we have the limit as x approaches pi of sine of x is 0. Okay? What about the third example? Can I just plug in negative 1 into this expression and be done and have the value of the limit? Well, that comes down to asking the question, is this continuous at x equals negative 1? Now remember what we need for a function to be continuous. The function needs to be able to be evaluated at c. You need to be able to find this value. It has to exist. The limit has to exist, and those two values have to agree. But look at this expression. Can we evaluate this expression at x equals negative 1? We're going to run into a problem, aren't we? Right here in the denominator, if I plug negative 1 into that, I'm going to end up with a 0 in the denominator. That's not good. That removes negative 1 from the domain of this expression. So I cannot find f of negative 1. So it does not exist. So that function, this rational function, fails to be continuous at x equals negative 1, so I can't plug it in. Not yet. Something else has to happen first. Now exactly what that is doesn't quite deal with this question, but we can certainly address it in a later video. But we can't plug it in. We can only plug in if we know what we're plugging into is a continuous function. And that's it. Hope that helps.